Hello, thank you for joining this webinar, Still Bending It Like Beckham. This is to highlight the issues of machining composite parts after they've been laid up. If you've got to physically manipulate those parts or distort them to get them to fit in the fixtures for machining, then there's an obvious error there in the process. And today I want to talk about how we can eliminate that error and work towards a more accurate and a more automated process for the post-machining of composite parts. My name's Aidan Wigham. I'm a technical account manager at MSP. I started 7 years ago as an applications engineer, traveling Europe and the world, installing our software and our solutions at customers in aerospace, motorsport, marine, oil and gas. And what connected all of these customers together was their requirement to drive quality not only in their parts but also in the processes that produce those parts. MSP are experts in on-machine metrology for CNC machines. We started in the CMM world and we've ported all of that knowledge and technology onto CNC machines. And it means that we can use the spindle probe to feed back information from what's happening live on the machine tool so that we can identify error and either eliminate it at source or correct for it. And it means that if we control all of the inputs into a manufacturing process, the output of that process is much more guaranteed and a lot more controlled. And we do that using our suite of products called MSP Perfect Part. You can see the modules there: Auto Clock, NC Checker, NC Part Locator, and NC Inspect. So Auto Clock is a piece of hardware similar to a tool setter for tools. This is an automated probe setter for the calibration and the checking of spindle probes. So that's a fully automated process, and it removes the possibility of manual error being introduced into the calibration of the spindle probe. Once you have a guaranteed calibration for that spindle probe, you can then use that probe to check the geometric performance of the machine tool. And that's how we do it using NC Checker. So that's an automated process, either run by the operator or fully lights out, to check the day-to-day performance of the machine tool to make sure it's in the tolerance required for manufacturing your parts. And then once all the hardware has been validated, we can introduce the part into the machine tool. And using NC Part Locator and NC Inspect, we can identify where the part physically sits in the machine tool and remove any positional error of the part with respect to its datum or work offset. And then once we've removed that positional error, we can inspect the form of that part and either check that the raw part is good enough to be machined or check that the machining operations have correctly machined the features. So the content of today's webinar, I want to start with some of the issues that we see quite often in over-constrained parts. These are the parts that are bent into the fixture to get the machining process started. Just highlight some of the errors that we see there. And then the rest is about the processes that we can deliver to gain an accurate and automated production process. And then at the end, we'll not only just be looking at the parts themselves, but also the molds and patterns as well, trying to make those as accurate as possible as well. So to start with, this is a typical fixture that we see on the shop floor being loaded into machine tools, where the surface of the fixture is the negative of the CAD surface, and then there are physical clamps on the top holding that part down onto that fixture. And there's a few errors here that get introduced by this type of fixture. One, if that part physically isn't correct to the CAD nominals, maybe there's plus material, then that part won't mate to that surface of the fixture correctly. Or if the part is distorted slightly, again, it will move on the fixture and won't be located correctly on the fixture. And if the clamps are pushing down against that distortion, it moves the part out of a free state. So even if your machining takes place in the correct place, once you release that part, the machine features won't be in the correct place on the free state of the part. And we can analyze that using NC part locator. And you can see here some of the errors that the software picks up. So in the first example here, you can see the red whiskers on the CAD show plus material in the center of the part. Now this is either due to the part in that area being too thick, too much material in that area, or the part is distorted so that that section of the part is sitting away from the fixture. And again, in the second example, you can see these red whiskers are now on the outside of the part. And again, that's either due to the part being too thick, being distorted in that area, or not locating down into the surface of the fixture correctly. And using the software, we can see that that part physically isn't correct for machining. If we were to machine that part, it wouldn't be correct for final inspection, and there's no point moving forward with that process. So how do we get around that? Well, we suggest that fixtures, you can see an example here that we've 3D printed to represent a blade, composite blade on a fixture. And you can see the contact points are a lot smaller, so it means that if there's any surface error on that lower surface, it has less effect on how the part sits in the fixture and doesn't create any distortion within the part. And it means that the fixtures can be a lot more simple. Because we're using the software to locate the part within the machine tool, the fixture doesn't need to do that job. The only job for the fixture is to physically hold the part to withstand the machining forces that the machining operation will impart into it. So that's some of the errors that we've seen before. So how do we get around that, and how do we use our software to automate and create a more accurate process? So the first thing is the automated alignment of the part. So composite parts tend to be quite complex parts with big curved surfaces in multi-axis, and it's difficult to find a nice orthogonal surface to be able to clock that part manually into the machine tool. So in the CAD CAM, you would write a probing program that probes the key features of that part. So either the datum features or the main features of the part. And you can see on the right hand side there the machine taking those points, and that data is transferred to the software to do the calculations and show the reports. And then in this report you can see the numbers on the left hand side, and on the right hand side we've got the CAD representation. Again, the red whiskers are plus material and the pink are under material. And you can see from that report and from the graphics that if we were to machine that part as it sits in the machine tool there, that we would machine that part incorrectly. There's too many errors to start with. So if we analyze those results, we can calculate a best fit alignment in full 6 degrees of freedom, a transition in X, Y, and Z, and then a rotation around A, B, and C. And you can see that represented in the simulation on the right-hand side. That is exaggerated, just so it's possible to identify in which directions the alignment is moving. And then once we've removed that positional error of the part, we can suggest what the form of the part is. So this is the predicted inspection report for that part. And you can see now that it's green, that part is good enough to be machined with that alignment active. And because that passes, the alignment is uploaded back to the controller, and that can be used in any subsequent machining processes or verification processes. So here we've got either pre or post inspection. So before you manufacture that part or do any machining, we can go in with the probe, activate the alignment, and inspect that part and make sure that the form of that part is correct for machining. And again, after machining, or even during machining, when you're creating features across that part, we can go in with the probe and we can inspect either the same features again or the new features that you've created. So you're either looking for distortion of the part or that the features that you've created are correct. And it means that when you've finished machining, you can do a verification to prove that as that machine is concerned, that part is correct and it can be removed from the machine. If you do identify any errors there, then the part is in the correct place for it to be either remachined or the errors removed. Sometimes we need to do iterative alignments on the part, and that's either for added accuracy or for localized datums. So this first one is for accuracy. If you've got a very complex part with a lot of curvature, or a part that's deviated quite far away from the CAD nominal, then we can do an iterative alignment. So we would probe again the same features, or a more accurate set of features with the alignment, the original alignment active. And then we can suggest and calculate a finer alignment that is more accurate for that part as a whole. And you can see on the left hand side another translation in X, Y, and Z and rotation around A, B, and C. And again, it gives you a predicted report with the positional error removed from that data set. And then the second iterative alignment is for local alignments. So if you've got features on your part that don't need to be constrained to the same datum set as the part as a whole. So we've got here an example, maybe a cover for an access point, or maybe a port for inspection. We can probe that feature and create a localized alignment just for that feature. So if you were to go in and just trim that feature or put some drilled holes in, they'd all be correct to that localized feature. Another example of a localized correction is countersinking. So on a composite part, it's very difficult to get the depth of the countersinks correct to the physical part to make sure that the bolt or the screw sits flush with the surface on top of it, or even if there's enough material underneath the bolt to hold the bolt in place. So what we do, as you can see here, we probe the part where the holes are to be drilled, or if the holes already exist, we probe next to the holes. And what we're doing there is identifying the localized error in that area of the part on that surface. And that probing result is passed back to the controller, and then the length of the tool is updated for each and every one of those countersinks. And it means that instead of having a bolt that sits proud of the countersink or sits too low, with this system you can get a nice flush bolt sitting within that countersink. Many of the parts that we see require machining in multiple operations. So the part is machined in one orientation and then rotated to be machined in another rotated, either 2 or maybe even 3 or 4 times. And what we see our customers previously struggle with is that the machining of these different sides don't always match up, and there's an error between the features that they've machined in different operations. So you can see here in this first operation, we've already seen how we would locate that part in the machine tool, and then we would do the machining. Here the example is the countersinks again. So we know that those features are correct to that part, but in this second operation where the part is turned over, how do we make sure that that alignment is correct back to that first operation? So what we're doing here is we're going to probe the same features that we did in the first operation, but in the second operation. So ideally we'd like to take exactly the same points, but that normally isn't possible. So here we've taken the edge points of that lower surface and then the end points of the part. And what that does is it aligns that part in the second operation, in the second orientation, back to the alignment of the first operation. And you can see again in the simulation what the alignment is back to those datum features from Op 1. And again it shows you a report and a graphic of how well that part is sitting on the fixture and the condition of supply. And it means that when we start machining, those machine features are in the same frame of reference or the same datum structure as the Op 1 features. We don't just work with the composite parts, we also work with the molds and patterns that our customers use to produce them. So for some of the larger parts, there might be multiple processes to produce the pattern or the mold, and it might be introduced into the machine tool multiple times between different operations or between different machine tools. So to be able to accurately align that part back into the machine tool, what we can do is include some datum features or some location features into that part. So here the example is 3 bores and planes, and it means that we can quickly and accurately align that part. It will probably take less than 5 minutes to get that part set back up to the machine tool and straight into the machining or the finishing of that part, or adding any amendments to the mold itself. And then once the machining of that mold has been carried out, again we can inspect it to make sure that the dimensions are correct for the parts that you want to produce using that mold. So that's some of the processes that we can help with, but the overall business benefits of those processes you can see here. One of the major ones is the improved health and safety. Because we're using the probe and we're automating the setup of the parts, and the inspection of the parts, you no longer require personnel, your operators or inspection, to enter the machine tool, which could be full of carbon fibre dust, to set up the parts or make sure that the machining has been correct. Again, because it's automated, we're able to maximize the return on investment of your machines. They won't sit idle while you're waiting for the correct personnel to start a job. That process is the same process every time, so it can run straight into manufacturing the parts. And again, because that process is so stable, your schedules are also stable. You know exactly how long that process is going to take. So it gives you a lot clearer idea of when you're able to deliver your parts and how you're going to schedule your personnel. Because you've got so much control of the process and of your machine tools, we can help you totally eliminate rework and scrap. So that totally drives down the wastage costs of the production line. And because you have more capability on your shop floor, you can tender for more complex or more valuable work. And then if you look at it from a sustainability point of view, I know a lot of our customers are now looking at their manufacturing processes from the sustainability point of view and looking to either save wastage or save energy and become a more greener and sustainable manufacturing process. Like I say, we already reduce a lot of the scrap and rework, totally eliminate that, and increase the uptime of the machine tool, so it's not wasting time and energy idling, waiting for the next process to happen. As a secondary benefit, we've seen quite often that automating a process can mean that that process can stay within the UK. It's not ported out to a low-cost economy, which means that the parts are transported a lot further around the world. And again, the programming of the part alignment and the part inspection, along with the actual machining programs, that can be done remotely. It doesn't need to happen on the shop floor. So that again saves a lot of energy in transportation costs. And because you can retain capability in-house, you don't need to subcontract more complex work to other providers, again reducing transportation energy. Here are some examples of some people that we've worked with in the past. You can see they range from aerospace, defense, to civil engineering, and also some machine tool providers. And here are some examples of the parts that we've made with these customers and partners. So starting with carbon fiber chassis for F1 and hypercars, and also aero packages for there. And then aerospace parts from the engine to wing structures to the actual internals of the cabin. So all of these parts either tend to be high value parts or complex parts, or there was a desire to be able to automate the production of these parts. And that's where we were able to help. So if you have any desire to introduce automation or sustainability or more control into the machining of your composite parts, please get in contact. You can see my email address there. I'd be more than happy to set up a free consultation with one of our engineers, just to have an online hour where you could talk about some of the challenges that you currently have, and our engineers will suggest some improvements that you could make or some different approaches. And if we do find that we could help you with some of our products, we'd be happy to create a free simulation video on some of the improvements that our products could actually implement. So thank you for your time today. And I think the last point just to make is that as our industry comes out of this lockdown that we've had for the last year, we've got a great opportunity to improve what we have and to build back better. And there's no opportunity like there is now. Thank you.